In the last video, we found the average rate of change over an interval. Remember average, and by the way, this was also the slope of the secant line. Remember that average and secant, those indicated two distinct points, and these were rates of change in y with respect to x, so that meant that the change in y was in the numerator and the change in x was in the denominator. And so now, and then we also noticed that if we did that over shorter and shorter intervals, we started with the interval from 2 to 4, and the average rate of change was 28. All right, we went to 2 to 3, starting at 2, ending the interval at 3, the average rate of change was 19. As we continued to reduce the size of the interval, all right, from 2 to a value that was closer and closer to 2, all right, the average rate of change seemed to be approaching some value. All right, to see what this value is, we'll need to come up with a formula for the average rate of change. So, all right, we're going to then now find the slope of the tangent line, all right, and what we'll call the instantaneous rate of change. So we'll start at the interval at 2, all right, and then the y value, as we saw before, was 8, all right. If we end the interval at an arbitrary value called, we'll just call it x, all right, the interval will be the y value, the corresponding y value will be x to the third. All right, so that x would have changed from 2 to x, or the change would have been x minus 2. It started at 2, ended at x. All right, the change in y would have been from 8 to x cubed minus 8. All right, and so the average rate of change in y with respect to x would have been the change in y, x cubed minus 8, divided by the change in x minus 2. Okay, now in order for us to look at this, what we're going to do is, we remember as the intervals got shorter, as this right end point got closer to the left end point, got closer to the 2, all right, this value seemed to be getting closer to 12. We'll see that that's indeed the case. We will need something from algebra that a lot of students forget, and that's how to factor the difference of two cubes. If we have a number a cubed minus b cubed, this factors into, the first factor would be a minus b, the second factor would be the square of a plus the product of a and b plus the square of b. We'll need that information in a second. So what we're going to do is we're going to find the slope of the tangent line, or the instantaneous rate of change, right, by taking the limit as the right end point x approaches the left end point 2 of the average rate of change, x to the third minus 8 over x minus 2. Remember, using our formula, with x playing the part of a and 2, 8 is 2 cubed, playing the part of b, this factors into x minus 2 times the square of x plus the product of x and 2 plus the square of 2, okay, all over x minus 2. Of course, the x minus 2's cancel, so we're simply left with the limit as x approaches 2 of x squared plus 2x plus 4. Now, as x approaches 2, this is a continuous function, so we can simply replace the x with 2, and this becomes 2 squared plus 2 times 2 plus 4, 4 plus 4 plus 4. This limit becomes 12. Remember, we suspected that it was approaching the value of 12, and indeed it was. Let's take a look at the picture of this. All right, So we have the tangent line, or excuse me, the secant line, all right, determined by the points starting with the left end point being 2 and over the interval for the left end point being 2 and the right end point being 4. All right, as we reduce the length of that interval now from 2 to 3, all right, remember that the slope went from 28 to 19. As we reduce the interval even more from 2 to 2.5, all right, from 2 to 2.5, the slope, the average rate of change, or the slope of the secant line, was 15.25. And from 2 to 2.1, remember now it was getting, you saw it was getting closer and closer to 12. Finally, if we reduce that so that we have no change now, all right, that right at the point 2, 2, 8, okay, notice these 2 points are the same, all right, the slope was 12. Now notice this is an interesting situation because the change in y is 0 and the change in x is 0, all right, but we still, the limiting value of that slope was 12. This line, since it's determined just by this 1.28, this line is known as a tangent line, and the rate of change now, all right, if we would go over 1, can't draw on this, all right, we'd go up 12, would be what we call an instantaneous rate of change. So we should point out here that now we have this situation. All right, we have used the point's tangent to describe the line. All right, and the word instantaneous to describe the rate of change, and this is because now it's determined by 1 point. Right? Okay, and this is now called an instantaneous rate of change. In y with respect to x. All right. Now, we had talked about this as being delta y over delta x before, but that's when we actually had a change in y and a change in x. Now, all right, this value that we get to 12 is a limit of a change in y over a change in x, but no change is actually taking place. So this is often referred to now as dy over dx. Again, the dy, which replaces the delta x because there's no longer a change, all right, is the, well, we call it a differential of the variable y, which comes before the phrase with respect to, and the dx is the differential of the variable x, right, which we use it again dx rather than delta x because there is no change. All right. In the next video, we'll look at a different format, a different way of representing this, of writing this.